because of your lab this week on optical instruments, I wanted to skip straight to this topic and talk about several different things which you will encounter down in here. We'll talk more about the eye and corrections to it, although I don't know if it's a part of your lab. You will be doing in the lab magnifying glass, and I think we're going to skip telescopes because it's probably not very much in most of our experiences to deal with a telescope. But we do use microscopes, you do certainly in your work. So I will try to talk more about that. So let's skip ahead to look at what we've been through here. And hopefully some of this is pretty much in your minds now. Now, the idea is that one of the major things we're trying to do is simply to magnify the size of things. For example, looking at bacteria under a microscope, or looking at a very distant object and trying to make it look better with a pair of binoculars. So the general idea is we're eventually going to see with our eye, in those cases. The other case you might want to do is actually record the image on photographic plate, say. Both of those instances require that the image that you get be a real image, because in both cases you're trying to, here's your eye, you're trying to create a real image on the retina, trying to replicate, say, an arrow here, to give you an arrow, the point of the arrow here. So it's a real image where the light is coming in to this point. If the retina were in here, the light would continue, and it would look like the light is coming out of that point, so that we call a real image, because the light is really there when we look at it. So that's one instance where we have real images, and we need them. The other case would be if you're trying to photograph something here, the light wants to converge to a point, replicating the head of the arrow in a incoming beam of rays, and focus at this point to give you a sharp image of this, and the light being focused on the photographic plate. So there you're dealing with real images. The other thing you can do, though, is you can use the fact that your eye is itself a lens. In fact, it's a compound lens. It's got the cornea, and it's got this adjustable lens in here that we talked about last time. The eye itself can do things to the incoming light that might help you. For example, the light actually might be coming from some kind of a virtual image, diverging, but then your eye can take the light and converge it. And if possible, do something like this. And that is to say, your eye will do the converging, whereas the image, the object in this case is over here, is a virtual object for your eye. So you can play tricks with that too. So those are the two cases we'll be dealing with. I have a bunch of slides that I passed on to you describing the eye in some detail. The interesting points being this adjustable lens in here. That's the one we care about a lot, and it has this remarkable feature of being flexible. Now, if your eyes are good, what happens as you age, however, is that this lens, whereas it's kind of a bag of jelly, or jello, when it's young, it stiffens as you get older, and it stiffens into one shape. So what happens is that even if you flex this ciliary muscle and you loosen the threads that are pulling on the lens is stiff, it doesn't change. So older people lose their accommodation. They can't see both in and out. They sort of have fixed focus. So that's when you end up seeing people with bifocals, because they're looking through one lens when they want to see far, and they're looking through another lens when they want to see short, because their eye lens, their natural lens, can't make that adjustment, this accommodation to distances. So that's why you'll see older people with bifocal lenses. Yes? Yeah? Yes. Well, it's not exactly. What that is more, the demo was this. We had this big mirror, and here was your eye over here. We hung the real flowers, upside down, shone a light on it, and then the light from it reflected here and formed a real image over here. So the light was actually sort of coming out of these points in all directions. So this represents a real image. And that's why, and what happens when the light reaches your eye projects back and says, oh yes, I see light coming from here, that must be a flower. So that's what happened in that case. Very, very good point. So that is a real image, and it's real because the light that you see coming from there really did come from there. Your eye collects it, focuses it right on your retina, and says, ah yes, flower. By the way, it's upside down on your retina, of course. Okay? Well, this is just interesting to see just what a marvelous mechanism the eye is. Okay, basic idea. Now the cornea. Cornea is interesting too. Sometimes people can modify the cornea by doing laser etching of the cornea to try to change its refractive properties, because it does a lot of the refracting of bending the light to pull it into the retina. And this is the marvelous piece, the crystalline lens, with its muscles and fibers to allow it to change its shape. And the point, of course, is that the amazing thing about this construction, I find, is that the design is such that the lens is as thin as it's going to be when you're relaxed. So when I'm looking at you, the ciliary muscle is relaxed. It's nice, so it doesn't get tired while you're doing your normal business. Reading was not the thing that this was designed for. If we did reading all the time, the muscle would probably be relaxed while you're reading. But most of the time, when we were evolving, we wanted to see at a distance. And so the muscle here is relaxed when it's narrow. And then what happens, of course, is the muscle gets larger when it's tense. And I just didn't do that well. And it relaxes when it gets, it's funny, it's a double think here a little bit. When the muscle is tense, the fibers relax because they don't pull as much, and then the lens gets bigger. And when it gets more round, its radius curvature gets smaller, and then it refracts more. So when the object comes in closer, the lens gets fatter, and you focus in and you hit the retina. Of course, the retina is always the same distance from the lens. So it's the camera here is the same size, as it were. What's changing is the shape of the lens to do that. If you ever come across a material that you can change its shape easily, especially with transparent material, you can change its shape easily with an electrical signal. you have the possibility of making an adjustable lens. If you could, say, take a rangefinder and such that you could take the range and adjust the size of the thing, that is, make it bigger, you've got a great invention. You could create an adjustable lens like your eye lens and put that in a camera, say in a cell phone camera, and such that it wouldn't have any moving parts. You could adjust the size of the thing. If you ever come across such a phenomenon, patent it right away. and then you can think about other things because you won't have to work anymore. But that's a nice thing to think about. Just how can you change the size and shape of something by a simple external means? Electric would be very good, because you get a rangefinder, maybe send you a signal, oh, she's 6 feet away, therefore the lens should be such and such a shape, send the signal, change the shape of the lens, focus. You'd have something good. Okay, so then I have a little picture. It's good to know. I mean, you're biologists. You may well know all this stuff, but I'm just amazed by it. And the accommodation idea is that as things get closer, the lens gets rounder and focuses sharper, more strongly, and keeps the object making a nice, clear image on the retina. There are some nice animations online. I suggest you look at those. And the word that you'll sometimes hear is a diopter, where they prescribe lenses. It's just the one over the focal length in meters. And the shorter the focal length, in a sense, the stronger is the lens, right? Because it's focusing sharper. The focal length is short. So you take one over that, it suggests the power of the lens. The diopter kind of indicates how strongly it focuses. Does that make sense? For example, plate glass doesn't focus at all, but the focal length of this is equal to infinity, because the focal length is sort of n minus 1 over r, 1 minus 1 over r2, and if it's a flat plate, the radius is infinite. So if that's infinite, the focal length is infinite, and the power of that, being 1 over the focal length, is 0. So that plate glass doesn't focus at all. Just diverts. I think you raised that point once. But if the radius is small, then the focal length is small, and you get more. We call that a more powerful lens. That would be the diopters. You sometimes see on your eyeglass prescription diopters. Okay, so we could talk about how the eye is corrected. Like if you don't have perfect vision, and they prescribe glasses for you, what are they doing? Let me the next slide shows it a little bit. Let's see. Well, they don't show the normal eye. In any case, the normal eye would be that if a person is looking at an object very, very far away, the light would come in as a parallel beam, and it would focus without a lens, without this external lens. This was an ordinary lens. It would focus on the retina, in particular on the macula, which is the most sensitive part of the eye, if I understand right. You've heard the disease macular degeneration. It's a bad thing, where the macula, the sensitive part of the eye, degenerates, and that's bad news. You lose your vision. But so that's part of the retina, the macula is. And so in a good eye, the light will focus right on here. Now, if you are here's the top one, far-sighted. What happens is that the beam's coming in, your own lens is a little bit too flat. Either that or your eyeball is too short, and the light focuses out here. It doesn't give you a sharp, it's kind of a blurry image on your retina. So in a case like that, you're going to need a lens like this to pull the rays in, because they're going too far, so you want to pull them in a little bit. We'll see just how you do that in a second, to make this beam that was focusing here to focus on the retina from a far thing. Now, if you're nearsighted, what happens is your lens is too fat. And so, again, by this argument, it focuses too soon, too much power, and it focuses here. So what you want to do is to spread the beam out a little more so that it focuses better on the retina. So here, what you want is to spread the beam out, you want to diverge it, so you put a diverging lens in front. Now, I'm not going to talk about astigmatism. That's a whole thing about, it's not obvious that your vision should be equal in all directions around like this, so you can have an axis of thing, but unless you're into optometry, we're not going to bother with that. Okay, and I showed you this model of the eye and its various deficiencies and corrections. Okay, so let's take this as an example, and the purpose is to actually define some terms. Let's say you have a myopic person, meaning nearsighted, whose far point, I have to define some words here. If you have a myopic eye, a very distant parallel beam will focus too soon. This is myopia. So it focuses too soon. Okay, but if you, that's for an object at infinity. But what happens if you bring the object in closer, that focusing moves out. You recall? The focusing moves out. So let me say, if I have my object over here, those rays will focus further out. And at some point, you'll be able to see clearly. Even a nearsighted person, if you bring a far distant object in, eventually you will see. Well, so this thing we call the near point. This is actually it's the far point. This is the furthest point that you can see something clearly. And this will depend on just how the lens in the eye is working. Okay, so the question is, what do I do to allow this person to see an object further away than that, say at infinity? As we said, the idea is that what you do is you put a lens in here, which will take the object that is at infinity and make it appear to be at the person's far point, because then you can see it. So what you're trying to do is take an object at infinity and make it look like it's here, and then the person can see it. So you put a lens here. In fact, it'll be a diverging lens. And to be fairly fancy, you could say, well, there's a distance between the front of the eye and the middle of the lens. Okay, we can put that in if you like. I think in the example here I said that's 2 centimeters. So it becomes just a geometrical optics problem. That is, we take the object at infinity and make an image at the far point. And I think an example I give here, the far point was, in this person, 400 centimeters. Okay, the far point. But you see, the image is on the other side of the lens. See, by our standard configuration, the object is here, the lens is here, and the image is here. We're trying to get an image over here, so that image is negative by the convention of so anything that isn't standard we call negative. So the image is the far point minus 400 centimeters from the eye. But it's actually 398 centimeters from the lens. And when we do the formula, 1 over s plus 1 over s prime equals 1 over f, those distances are measured from the lens. So the image here, instead of being is actually 398 centimeter from the lens. So that would be the image distance, S prime, 1 over minus 398 centimeter. And the object distance is actually infinity. So that's nice, that drops out. And that would be 1 over f. So the lens that we put here will be of a focal length minus 398 centimeters. And that agrees with our intuition that it wants to be a diverging lens, because in fact the sign came out negative. So that's the answer there. Okay, now there's another example here which is explained in some detail, so perhaps I won't go through it in gory detail. There's another one here. But it's the same idea. You're just trying to get an image where the eye can see it, whether it be far place, you want to get an image where the eye can see it at a far distance, or if it's near, where it can see it. There's also a near point. That is the nearest point where your eye can see. We know that, because typically it's considered to be 25 centimeters. This is your sort of standard young eye. 25 centimeters from the eye is the nearest place where you get a clear image. 25 centimeters is 10 inches, isn't it? So roughly 10 inches from the eye is about where a healthy eye can see. A nearsighted person might actually be able to see closer, because his eye has a stronger focusing power, so he can take that light which is diverging from a point here and pull it in, so he can actually see something closer, and things like that. So I think you can go through those examples by yourself. If you have any problem, let me know. The other thing, though, is people get a little bit clever and start using the second type of system, where you use virtual images as your image that you're looking at, and you can get magnification from that, because we saw that if you have a lens with a certain focal point, if you bring the object inside the focal length, what you get, let's do our ray diagram, right? Let's say the focus is here, another focus, and we've got one ray that passes through here, we have another ray that passes through here, and what's going to happen is that you get a virtual image over here on the other side. But the interesting thing, of course, is that if you bring the object really close to here, this virtual image gets to be very, very large. Let's see, I think I might have some this animation here is very good. I hope you'll play with this sometime. It's really a wonderful thing. Where if you bring an object, here's the focal point, but I'm going to bring it inside the focal point, just inside the focal point. The rays are pointing way out here. Let me see if I get some more rays. Many rays. Okay. Well, it becomes more dramatic if I bring it in. You see, here it looks like the rays that come through the lens, they look like they're focusing about here. But if I bring it close, just inside, the rays look like they're starting much taller. So when they come into your eye, they will occupy a much larger fraction of your retina. And so the image will occupy a whole section of your retina, and the object will look much larger. But your eye is doing the work here. So what the point is to, here's how you do it. You bring a lens. This is a magnifying glass. This is how a magnifying glass works. A single lens. You bring that, you put the object just inside the focal length of this magnifying lens, and then you put your eye over here. And your eye will collect this light, and it will think that the image is, the object is way out here. And so it will give you a magnified vision of that. So that's the trick we use. At the last stage of these things, if you want to see the thing with your eye, you make the last stage of a multiple stage thing where you put an image inside the focal length of a converging lens, and then you get a big magnification. This other simulation here from France. Let's see if I can get it on screen. Can you see it? Oh, I didn't mean that. Nope, I didn't want that one either. Let me put it away for the moment. Yeah, okay. This is cute because actually it starts out looking like a microscope, and then it exposes the parts. So what you have is an object here, just outside the focal length of what's called the objective lens of your microscope. And because it's just outside, it creates a magnified image. That's one stage of magnification. But the other stage that you do is you put that, now that image becomes the object for another ocular lens, the one in your eye. And so if you move that ocular lens, try to move it, see if I can grab it. Monsieur oculaire, why don't you move? Maybe I should speak French to it. Bougez, monsieur. Alors, pourquoi pas? Vie de réglage. What am I doing here? I'm moving. I should have been able to move this thing, no? Let's see. Why am I changing that? Should be able to move the position here. Let's try this. Turn it, no?